Out of curiosity, how many people here were at Contest University? Ah, okay, wonderful. You guys are now going to end up tutoring everybody else because there's going to be a couple things in here that you'll see from there. I also will be able to kind of reinforce some of the stuff you've already seen. But really what this is lessons learned for amateur radio. And it really has a lot to do with the last storm, that big storm, the G5 that we had. You guys are in, honestly, you're in like the perfect place because all of your expertise and your experience will really help the next generation of, believe it or not, precision farmers. And you're about to see, how many people either have a farm, know somebody who has a farm? Anybody in the, yeah? Did anybody groan during the Gannon Storm, what we call the Gannon Storm, the May 10th storm, 2024? No? Okay. You're going to see a lot of folks that did, and you'll see why. And it's actually a bit more, I think from this point of view, you're going to be the ones that will be nodding, saying, yes, I completely understand why, while the precision agriculture folks are still scratching their heads. Because you guys are on the front lines of space weather. I've said it forever. Right? And those of you who know me, it sounds like a broken record, but it's really the truth. So let me see if I can get this full screen. No? Does this go full screen? Do you see? No, you still see the... How do we do this? Hold on. Yeah, but it'd be nicer if it was like an actual full screen here. I got a moment, so I can probably figure this out. How about this? How's that? Yeah, a little better. Okay. Yes, I went to college for that. All right. So let's, before I start, by the way, I do want to give special thanks both to K3LR for allowing me up here to talk with you wonderful folks again, and then also to my colleagues, Dr. Terry Griffin, who you'll start knowing a little bit more about, Janelle Shank, who's a GIS expert, as well as a lot of other space physics colleagues of mine for some of the data that you're going to see here. A lot of movies, so it's going to be a lot of eye candy. All right. So just starting off, the space weather stakeholders, right? This is a slide I've shown for quite a few years now. It's coming close to a decade. And amateur radio, right, the emergency responders, you guys are at the top of the list. You're on the front lines of space weather. You sense literally everything the sun does, whether it's a solar storm, right, a CME, or a radio burst or a solar flare. You guys are hearing it, dealing with it, having to mitigate through it all the time. But you're not the only ones, right? With some of the emerging markets, in particular, we've got drones now. So there's a whole emerging market of GPS and GNSS technology, and you're seeing a little bit of precision farming in there. And we'll talk more about that in a minute. But of course, the Aurora community, the tourism community, the space tourism community now, Hotel ISS, that's becoming a big deal. SpaceX, of course, right, Starlink, they were falling out of the sky a few years ago, and during the big storm in May 2024, they really had a hard time staying in the sky. They fell out a lot faster than they expected to. But of course, we've got the old players, right, the Department of Defense, Homeland Security, the FAA, Department of Energy, and then we have also the news and the weather broadcasters and all those folks who are coming online. But now we have to add yet a new one. And this is what they call the smart agriculture market. And the reason for this is because GNSS-enabled agriculture tools are taking over. And this includes not just planters and harvesters, but drones, right? They do soil management, they do water management, they even do livestock management. It's amazing how much data they uplink and downlink at any one time. Okay. So why do we care? Well, space weather impacts, you know, again, the list is growing. There's not much at all, really, just these little things, right? You guys are at the top, amateur radio. But we have satellite radio and TV. We have satellite internet, the Internet of Things, airline communication, right? FAA really cares a lot. National electric utilities, power grids. I could go on. Emergency or disaster relief, right? Anything that runs on GNSS, drones especially. Precision agriculture, right? That's a new one. Financial markets, precise timing applications, Aurora tourism, space tourism, and now cloud-based services, storage and operation, including AI. That's going to be another big one because of the amount of energy they require. But here's the thing. All of this is interconnected, okay? And this expertise really can be kind of cross-wired. And so I want to kind of give you a sense of a paradigm shift. Because when I just pull out just a few of these communities, okay, these are some of the basics, really. Here's amateur radio once again. I'm sure all of you should be at least in this group, right? But how many here also do geocaching? Anybody? Yeah, quite a few. Well, there you go. What about emergency services? Right? There we go. So you're already a part of two different types of communities linked by expertise. Well, believe it or not, the Aurora Chase community, the Storm Chase community, that seems pretty easy, photography, right? But you wouldn't think that you're linked to them. Well, actually you are. You're linked to all of them. Aurora photography has aurora propagation. You guys hear it, right? Sometimes even call it picket fencing. We, myself included, because I've looked at aurora, we call it picket fence. We actually see the picket fences that you guys hear, okay? So it's called the same thing. Of course, Skywarn and spotter networks, that's pretty easy, right? Because a lot of these spotter networks, they require you to have a ham radio ticket in order to even be part of their club. GPS operator, search and rescue, public safety, and certificate of authority operations, of course. And aurora chasing. A lot of aurora chasers anymore are drone photographers. So they're beginning to understand GPS technology. So you're really forming a highly skilled super community connected by expertise. That's the first thing, okay? Your nearest neighbors are likely multiple categories in here. But you're also connected by weather, right? Picket fencing, we just talked about that. Night side signal disruption. For amateur radio and storm chasers, well, radio blackouts and HF signal disruption, they care about that. You've got collision avoidance and loss of satellite log when you talk about GPS operators and storm chasers, because they share that particular aspect. And signal scintillation, right, which is this twinkle, twinkle, little star. And this affects GPS dramatically. And that also causes drones to drift. So they can't hover like out-of-ground hover and just hover there. So if you're doing any type of reconnaissance, it becomes very, very difficult, especially with photography. And of course, when they all kind of come together, this is where space weather and terrestrial weather collide. So you're not just an amateur radio operator. You're part of an interlinked, huge community. And a lot of these people know the same things, or at least similar things, or they know the same phenomena you do from a different angle. And that can be exploited tremendously to your benefit, as well as to theirs. Okay, so keep this kind of super community in mind, this mindset in mind as we move forward through this talk. Oh, and one other thing. These have gotten really, really good, because now not only do you guys know space weather, but the public knows it too. But it's through a different lens than we would expect, right? These cameras have gotten so incredibly good that they can see aurora when your eye can't. So everybody and their mother and their grandmother's mother and their grandmother's mother's mother, right, has seen aurora. At least they can photograph aurora even if they can't see it with their eyes. And so that makes people nervous, doesn't it? Because they think, uh-oh, what's the sun doing? The sun must be doing something very different, because I've never seen aurora like this before. So this public knows space weather, but thanks to pop culture, right, because they'll run with this, superstorm, big superstorm events, right? Sometimes some of you might know what the Carrington event is. These are the big, massive, massive superstorms. They have taken on an entirely new meaning. This is the lens that pop culture sees, right? Today, we have pet names for it. We have mega flare, kill shot, micronova, power grid destroyer, Armageddon from the sun, God's wrath, black swan. There's a whole host of names. And it's basically any space weather event that spells doomsday for Earth's weakening magnetic field. You might have heard about this. All of our technology, and ultimately all life on Earth. And if you don't believe me, go to YouTube and look up Solar Attack. It's right there. You can actually watch this movie. It's got Louis Gossett Jr. in it. You actually can watch this movie and you can tell what a coronal mass ejection is. They actually call it, this is a coronal mass ejection, guys. Rocks from space, right? Hitting playgrounds and kids and knocking statues apart. I mean, come on, right? But there's a whole generation of people who have never seen anything that the sun, has no idea what the sun can do. Most of you guys remember cycle 22, maybe cycle 21, maybe even cycle 20 and 19, when solar flux and sunspot numbers were easily over 300, 350, and you can get around the world propagation with 5 watts. Remember that? Those days are coming back, okay? But a whole generation of people don't know that. So really quickly, let's talk about the sun, because I'm going to get you caught up in where we are in the cycle, because this is really important for what's coming, okay? And I'll just do this quickly, so don't worry, it's not a big tutorial. So we have solar flares. That's the first kind, right? This is what I call when the sun screams, because the sun is screaming in electromagnetic energy, light, right? Takes 8 minutes to get to Earth, and it gives you a radio blackout, okay? That's only on the day side. Now, we also have solar storms. These are coronal mass ejections, if I can get this to play. Oh, it didn't. Why did it find the media? Okay, well, this one didn't find the movie. That's frightening. Should have. But you can see it. It's that loop of material. And if the movie would have played, it would have played all the way out. And then you get radiation storms. I hope it can find this one. Nope, media can't find that. But it can find that one. I have no idea why. Okay, so radiation storms, if those of you who know what DRAP is, that's a model that gives an indication of whether you have solar flares or big particle storms. And that's what you see in the red here. It's also what blinds coronagraphs. So you're seeing a blizzard. Sorry, I couldn't have it play for you. But it's a blizzard that literally makes stars, these false stars, all over the entire coronagraph. And it does this to lots of other optical instruments as well. In fact, it even does it to astronauts' eyes. So when they're up in space, this is what they see during a big radiation storm. That's kind of frightening, right? But not all of this stuff happens at all times of the solar cycle. Sometimes there certain phenomena dominate, and that is where we come to coronal holes. So you can see this and see it's hardly playing. I hope this doesn't cause a problem for us for the rest of this talk, but you can see that coronal hole, hopefully. That is not the sun dying. It's the solar dynamo is not going out. The sun is not splitting in half. It's not losing its light. It just happens to be cold in that region, so it doesn't emit light. It also lets plasma fly out fast to get away from the sun so it doesn't heat up. So that's why it's dark, okay? But what we get from that is fast solar wind. And when fast solar wind hits the slow solar wind ahead of it, it creates a big bow wave, just like a boat going through a river, right? You plow through it, you get a bow wave, same kind of idea. And that can actually mimic a big solar storm. And these coronal holes, this is what's coming. This is what we're beginning to see. So let's talk about where we are. See if I can get it to move, okay. So where are we now in the solar cycle? Why would we be seeing coronal holes? Well, has anyone paid attention to F10.7 recently? Anybody notice the big drop in F10.7 flux recently? Yeah. Propagation is not so good right now, is it? Yeah. Well, welcome to the declining phase. So we went from about 160 down to the teens, 115, 116. Those of you who recognize it. Yes, that is a signal that we really have gone into the declining phase. So we went up through the ascending phase. We had a very short maximum, strangely enough. We actually are about 6 to 9 months ahead of where we thought we'd be. And now we're beginning the declining phase. You can see us right here, okay? So for those who think that there's going to be a second peak, a second maximum, no, we're done. So we're going to be climbing down. And sadly, if the linker predictions are correct, and these guys are the ones that actually indicated, they actually predicted correctly that this was going to be a larger cycle than cycle 24. So these colleagues of mine are really on it. If they're on it this time too, we have until about mid to late 2027 before the solar flux drops below 100. So get your QSOs in now. QSO, right? Because things are going to drop pretty quickly. All right, so what does that mean? Well, it means the sun kind of looks like this right now, right? That's a coronal hole, okay? You can actually even see it in the synoptic map. And so the declining phase is a very complicated phase because it's not just about active regions and solar flares anymore. It's now about fast solar wind. What's really happening is that we have a new cycle that's already established itself and the old cycle's fading. So it's kicked the polar coronal holes out of the polar regions and down to equatorial regions, down to where, and that's why we're seeing them, because that's how the sun is shedding them. So the next 1.5 to 2 years, we're going to be dealing with this, okay? But it gets very, very active, believe it or not. It's the most dynamic, the most complex period of our solar cycle. So what are they? As I've explained before, they're dark areas on the solar surface that can be seen in certain frequencies of extreme ultraviolet and X-ray. Not all of them. So like the red sun, they're not there. You won't see them. But you see them in the bronze sun, as I show a little bit, and even better in the pink sun, okay? They have a lower density and temperature compared with the surrounding corona, and if you can see the magnetic field lines, I know the screen is really small, but if you can see the magnetic field lines coming out of the pink, that's the white lines that streak out. The ones coming out of the dark, they're all just straight lines that go straight out. The ones coming out of the bright loop around. Those are jailing plasma underneath it and not letting it get out. So that's why it's bright. It's because it's had time to heat up. Okay. So the dark areas correspond to plasma that can stream straight out because the magnetic field doesn't jail it, it lets it out. And so that corresponds to regions of open magnetic field, fast solar wind. So when you see them, expect fast solar wind. And like I said, during the declining phase, they come down into the lower latitudes where we live, because we live right in what we call the ecliptic plane, right at the very edge. So why is it interesting? Well, believe it or not, this is when activity peaks. So you thought the solar max was when we got the most activity. Not true. We actually get it now. And if you look at the plot up on the left, or on the right top, you'll see sunspot number at the top. Hopefully that is reasonably familiar to you. Cycle 20, cycle 21, 22, 23. But then the two panels below, one says small, one says medium. What we're talking about are storm sizes, so storms at Earth. The black line is coronal mass ejections, big solar storms, the big eruptions, right? The red line, however, are fast wind streams, okay? Notice the black line, if it peaks, it'll peak right on line with the sunspot maximum. So if you'll see those peaks rise just like the panel above it does. But if you look at the red line, that's the fast wind streams. Notice it's offset. It's offset just a little bit. I don't know if I have a laser. Do I have a pointer? I don't think I do. I don't know if you guys can see my arrow, but if you can. So here's, let's say, solar maximum right here, okay? Notice this red line is offset. The peak of it is offset. It's actually in what we call the declining phase. And again, the next cycle, same thing. Next cycle, same thing. So storms that aren't huge are the ones that will peak now. And why does that happen? Well, it's because we've got these persistent coronal holes. Look at this. This is from 2018. This was August. This is September, October, November, twice in November, and December. What is this? This is a coronal hole surviving its far side passage and coming back around. Because every 27 days, that the sun rotates one full solar rotation from Earth. So the same coronal hole is surviving, okay? That means every 27 days, we get a storm, right? Which means basically it's just bad all the time, right? They're not the massive, massive events, but they can be strong. In fact, if you're familiar with KP, right, this panel here shows active conditions. This shows a G2 level storm, so moderate storm. This is the next month we got a G1, then back to a G2, then back to active, then back to a G1. 6 months in a row, bam, 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 bam. We are just pushing on that swing and making it go higher and higher and higher, okay? This is why we get active condition, or why we get so much activity during solar, or the declining phase. The thing is, this solar cycle has outperformed solar cycle 24 by a lot. The fast wind streams are faster. So instead of getting G1 to G2, we're going to get G2 to G3. You get to a G3 storm, you're having problems. Even the farmers are having problems, okay? That's what we're going to be seeing. So let's see if I've already said all this. But the nice thing, one thing I didn't mention, is that during the declining phase, as you're already surmising, space weather becomes a bit more predictable. It's my favorite time. I don't have to be wrong all the time. For those of you who know, weather's terrible, it's awful. Space weather's even worse. So I actually get to be right part of the time because I can actually tell you when these things are coming. And even crazier than that, sometimes you see that one coronal hole, on the opposite side of the sun, there's another one. So now you're not getting storms every 27 days. You're getting storms every 2 weeks. See what I mean? This is why satellite operators hate this period. This is when satellites fail because they're constantly getting the radiation belts pumped, okay? We're also getting our upper atmosphere pumped. Get ready for some sporadic E, guys. So sporadic E should be a little bit better than it has been. Okay, and we're climbing down off of solar max, plus we're going into this declining phase where we're getting lots of particles being shot into the Earth system, and that helps to seed, again, create sporadic E. Okay, let's see what else is here. So for radio propagation, knowing what kind of fast wind that you're going to get is crucial, and this is what I taught at Contest University. So seek out people at Contest University because they know the physics behind what I was talking about. But for those at Contest University, remember, here's the shortcut once again. If you want to know when you're going to have stormy weather, when, in other words, propagation is going to be bad from a particular coronal hole, from the fast wind of that coronal hole, all you have to remember is snap. Spring equinox, look for a negative coronal hole, negative polarity. That will give you storm. In the autumn equinox, look for a positive polarity coronal hole. That will give you storm. Anything outside of that, you're good. And if you want to know what I'm talking about, if you go to the Space Weather Prediction Center and you look at their synoptic charts, they map out these coronal holes, and you will find in them a dash or a plus, meaning a negative or a positive. That's the polarity you pay attention to. Okay? So you can actually tell a priori, just looking at that coronal hole, whether it's going to be southward fielded Earth causing storm periods or northward fielded Earth not causing storm periods, but actually helping radio propagation. So seek out your CTU fellows. They'll show you the details. Okay, so let's now talk about this, okay? Because now we're moving into this active period. I hope I've given you a sense that activity is actually picking up now. And let's talk about the superstorm producer back in May 2024, because there's a lot to learn from it. You guys might remember this. This was old region 3664, but it really wasn't one region. It was actually 3 regions. This is why it was such a monster. It was because it started with region 3664 and 3668. This movie will replay, so you'll see it again. And then there was a 3rd region in the middle. If I can get the thing going. You see this right here? That region merged the 2 together, and Swipsy just dropped the name 3668 and just called the whole region 3664, but it was 3 regions. This region, or this monster region, fired 10 X-class flares, including the largest of this solar cycle, and caused a G5 level superstorm, which was the largest in 20 years. Okay. By contrast, solar cycle 24 didn't have a single G5. We've already had 2 this cycle, and this is not even that strong a cycle. So let me just run through. You can see here's that monster region on the disk, and you can watch it. We'll watch it fire solar storms. It was getting really nasty right about here. And I'll see if I can capture all the storms. There was 1. There was 2. So you see 1 halo in the coronagraphs, 2 halos. We're not done. There's 3 and 4. 1, 2. We'll go again, I think, right in here. This might be 5. There's definitely a big one, 6. That may be 5 or 6 right there. That's another big halo. 7. I think that might be it. Okay, so if I play this way, I have them labeled. There was 1 and 2 right together. 3, 4, 5. Here it goes, 6 and 7. So we had a pancake, a 7 stack, right, of pancake coming at us. This is what caused this huge storm in May. It wasn't just one event, and that's typical with these big, ugly beasts. They don't just fire one thing at you. They just keep firing all the time that they're in Earth view. Okay. Now, what happened during the storm? And the reason why we call it the Gannon Storm, by the way, is that one of our very important colleagues, she passed away like just a few days before the storm occurred. So our whole community calls it the Gannon Storm. So if you want a lot of scientific information, by the way, or journal articles, you can just type Gannon Storm and you will find a whole bunch of stuff that you probably won't find in other periodicals that might, just give you articles and stuff. But yeah, her name was Jen Gannon. She was a wonderful gal and dealt with magnetometers. So here's the interesting thing. This is where it starts hopefully getting your interest up. Anybody here do auroral propagation at all? Anyone from an area that does? Anybody you know anybody who does? Couple? Okay, good. This might intrigue you a bit. So the aurora from the Gannon storm was visually incredibly disruptive. In fact, Chris Wickland put together a Google map, and you can get it from that QR code right there at the bottom. This map has all these pinpoints of places where aurora was seen. And not only does it have that, but it actually, if you click on the pinpoint, you will find the picture. It will pull up the picture. So you can see that aurora. But the thing is, it's not just green, or what we called green streamers or discrete aurora that you see here. It was the whole gamut. There are all different types of aurora. We have things like streamers. We have in the auroral oval. We have all sorts of little features, sure, as you can see some here, right? But we also have pillars. We also have a SAR arc. We also have something called Steve. We also have dunes that live in the sporadic E layer that have mesoscale structures about 45 kilometers apart. All of this stuff affects how auroral propagation occurs. So while photographers were being able to pick the aurora out, and they've even got color-coded, you can see with the pinpricks being slightly different colors, they were picking out where a different aurora was being seen. And the SAR arc, which is more of a diffuse aurora, was at very low latitudes. So the thing is, what does that sound like then? If you're doing aurora propagation, does all aurora sound the same? Or is there some difference? Has anyone ever checked? Has anyone ever thought about doing that? Right? Well, now you have an ability to, because the aurora photographers are everywhere. I mean everywhere, right? I'm one of them now. So you have some ground truth visually, so that while they're looking at some synoptic view, you're piercing it and refracting off that layer. So there's some really not just interesting science, but some interesting information about knowing perhaps what kind of aurora is the most troublesome, what affects the signal the worst, and who might benefit from that? Well, precision farmers, but we'll get to that in a second. Whoop, if I can get this to play. Oh, this isn't going to play now? Okay, good. So this is the live MUF V7 from G7IZU and G7RAU, who have put this out consistently. And this is the auroral propagation that was gone through contacts. There was auroral propagation clear down to Turkey and clear down to Florida during this storm. So anyone who says that they never do auroral propagation because it never comes far enough south, you might get a chance, especially as our sun wakes up and they start sending more storms like this, okay? And for those who aren't familiar, the horizontal wings, so they have one contact and then they have these horizontal wings that show where these conics show where the latitudes at which auroral propagation and auroral scatter is occurring and where propagation would be possible. But again, you can see it goes from very high latitudes to very low latitudes. What kind of aurora were they getting? What kind of aurora were they using to propagate? Guaranteed it wasn't all the same. We know that from the pictures. But these are actual contacts, so it'd be really interesting to know. Because here's where things get crazy, okay? We have GPS, we've known this for years, that GPS signals get scintillated. So the twinkle, twinkle, little star story is true, right? It's beautiful when you see it in the stars in the sky, not so great when it's your HF rig or it's your, right, or it's your GPS signal. Because with geolocation, what happens is that you get indicators that you're all over the place. As a matter of fact, I know aurora chasers who actually use the GPS on their phones and wait for it to go crazy in order to know that they're near aurora if they can't see it in the sky. So they actually use the scintillation as a tool, right? They're doing over the horizon in a sense. It's not much different, right? All right, so here's what happened that night when the Gannon storm first hit. Okay, we had John Deere reporting on Friday, May 10th, if you can see this. It says, please be advised that there is a significant solar flare and space weather activity currently affecting GPS and RTK networks. RTK, for those who don't know, is kind of like an augmentation network. It kind of helps when GPS isn't giving them the precise enough numbers, and you can have a base station on your farm in your area, or you can get it from satellites, or you can get it from a network of a whole bunch of base stations all over. So there's different ways of getting RTK, but it's a correction network, okay? So they were having problems with not just GPS, but also their RTK network. It says the severe geomagnetic storm is the worst since 2005 and is forecast to continue throughout the weekend. We found that the best course of action at this time is to shut off RTK and use a grace period for SF2 and SF3. That's the Starfire 2 and 3. Those are the satellite constellations that were also supplying this. They said this will eliminate any of the conflicting corrections that the machine is receiving from the base station due to the geomagnetic storm. And GPS accuracy will likely still be reduced, but we apologize for the inconvenience. Well, shortly thereafter, they had to get another update and said, forget it, never mind. Don't Starfire 2 and 3, they're awful, the whole thing's awful, we just don't know what to do, we can't find a correction. And they said, we strongly advise you to keep an eye on your guess rows. Meaning as you're planting, because this was planting season, make sure you try to steer straight, okay? Now, the sad thing is that during this period, it was like a perfect storm. There had been horrible weather for the 2 weeks or 3 weeks prior to this, and there was this one weekend that was clear skies. And so all of the farmers in the Corn Belt went to go plant their corn because this was the last week that they could get in before their insurance cut them off, and they started getting penalties. Okay, so they had to plant this weekend. And this is when the storm hit. So they were already in trouble. But here's the thing. When Deere says keep an eye on your guess rows, they also added this. When you head back into these fields after you've planted, to cultivate, dress, side spray, all this stuff, harvest over the next several months, we expect that the rows that you planted won't be where the autopath lines think they are. So this will only affect the fields that were planted during the times of this reduced accuracy, as they call it. It's most likely going to be difficult, if not impossible, to make autopath work in these fields as the inaccuracy is most inconsistent. So in other words, for the rest of the harvest season, you're going to have trouble because everything's basically lost. You're kind of on your own. And I've learned a ton since then. But let me go back. I'm going to see if is this mic live? Yes. I couldn't, they didn't do the audio, so I'm going to give you audio here. And hopefully you can hear this as he talks. I'm going to try to turn it up as much as possible. Okay. Whoop, if it'll play for me. Come on.
I'm planning, going through the field, 10 miles an hour, as I always do. My tractor goes, I go, whoa. I slam the brakes, pull back on the stick, pick up. I'm like, that's not quite right. And then it goes, RTK signal found. I'm like, huh, strange. Try going again, same thing. So I just pick up, drive to the end, shut it all down, restart it. Acted fine. I came back on this pass and did the other half of it from the other side. I'm getting lined up into this one. I'm perfectly lined up, and it said I was 5 inches off. And then it jumped to 20 inches, and then 25 inches. So I start making phone call. There's solar flares from the sun, and it's affecting us. I don't know what hasn't happened to me at this point. I mean, solar flares of the sun screwing with my RTK? Are we being serious? And there's no way to know when it's going to be over. So.
That's the millennial farmer on TikTok. So this was repeated over and over and over again. I have many more examples of this if you'd like to see it. And it's not just with the May storm. But this is how completely clueless they are, that this could even happen, right? And I feel for them. I really do. But it gets worse. So imagine that happening farm to farm to farm, over large swaths of the continental United States. The news from this hit not just agricultural, rags, but actually ended up going to the New York Times. It became such a big deal. But I just grabbed this one because of like I said, I got a whole choice of different articles I could have shown. But this one really spoke to me. Because I say geomagnetic storm scrambles tractor navigation systems. I mean, they had stories about tractors literally chasing their tails. But, it goes over and over. But this is what really got me in this particular article. And I have it circled here. It says, if anything came from this, it's the importance of being proactive in protecting our food system and having a response plan in place to avoid large-scale disruption. Uh-oh. So this was something that got me really, surprised me. So I started working with an economist named Terry Griffin. Now, Dr. Terry Griffin is from Kansas State University. He's been doing agriculture all his life, and he always looks at impacts due to weather and other things, always financial, because he understands how this propagates over the course of a harvest season. And even NASA at this point, Terry Griffin is now part of the Space Weather Action Group. This was a big surprise. It was a huge pivot by NOAA to include Terry onto the SWAG, because the SWAG reports to the White House. Okay, because we're trying to understand space weather with new technologies and really get a handle on how space weather affects all of them. So NASA published this just recently, and it's what NASA is learning from the biggest geomagnetic storm in 20 years. Okay, storm consequences. You can read all this stuff in all sorts of places. But Terry says not all farms were affected, but those that were lost on average about $17,000 per farm. 17 grand. This is just for a couple days, because it propagates. The problem is they have these combines and harvesters that are meant to have perfect GPS rows, absolutely perfect. So when they go to harvest now, if the rows aren't lined up, and they had planted 8 rows, or they planted 12 rows, but their combine only does 8, and then they've got these things that are offset, the rows have to be dead on so that they can continue harvesting. Or if they're doing things that are planted underground, they have what are called inverters, and they have to dig into the ground to get, let's say, peanuts or sugar beets. I think it's sugar beets. And if their reckoning is off, well, they dig and hit nothing, right? So the yields drop and drop and drop and drop. So Terry had said, this isn't catastrophic, but they'll miss it. This is like a wake-up call for the agriculture community. It's a wake-up call for NASA. It's a wake-up call for all of us who care about space weather. And, we've known about navigation and radiation and flights and all that kind of stuff, but this one kind of really caught us because it's talking specifically about our food supply. Now, even spaceweather.com got in on it. Solar storms are driving the farmers crazy. You can see the headline there. They're talking about our tractors acted like they were demon-possessed. Okay, some of them lurched to the left, to the right. You can even see the picture of the corn rows. See those corn rows? What drunken farmer was doing that, right? That is what AutoSteer did for them, and GPS did for them that night. And they said May 10th wasn't the end of it, because we had another G5 in October that same year, last year. Again, farmers are like, we're getting hit by this. This is a problem. And now they're kind of going back in their head, and they're realizing all the times in the past that they've gotten hit, and they didn't know what it was. And they just kind of blew it off like, oh, it must be my equipment, must be this, must be that. Now they're thinking, was that space weather? And now they're beginning to recognize, because I've seen more and more and more reports during G2 and G3 level storms, which is what I saw in solar cycle 24 just a few times, because I'd have the savvy farmers say something, but now they're all beginning to say it. And they're all kind of like pale in the face because they don't know what to do. So I've been working with Terry. We've got a paper out that's published in Kansas State University, and I've worked with other people. But here's part of what's really cool, if you really want to dig into this and the economic damage. But I pulled out one slide, one diagram for you, because I want to really hammer home some stuff, and this is where your expertise comes in, okay? This is one plot. And you can see what we've got plotted on here are storm events for an entire solar cycle. So you can see solar cycle 17 up here, 18, 19, 20, 21, 22. So hopefully you can see that. And it's January through December. So it's each year just kind of plotted on top of each other. And these are storms that are G2 to G2 and above, okay? What we call KP7 and above. So moderate level storms, not even huge ones, okay? What's in green and gold? Green is the planting season. Gold is the harvest season. And for those of you who remember, I told Terry very early on, I said, you guys do a lot during the equinoxes. You plant and you harvest in the spring and fall equinox. Uh-oh, because the CTU members know, we just talked about the equinoxes. That's when space weather peaks. That's when you get the biggest storms. In fact, as you look at the gray and the blue bars on any of these cycles, right, you see that there's a peak in the fall and a peak in the spring. Again, peak in the spring, here's a peak in the fall, and you see it kind of dips down during the summer period. Well, those are the solstices. We don't have, space weather kind of minimizes at the solstices. It's just how Earth shakes hands with the sun. So this is a natural phenomenon. We know about it. It's called the Russell-McFerrin effect. We've known about it since the 70s, okay? But it just so happens that it's the worst possible thing for farmers. And so there's the Gannon Storm right there, okay? That happened at the beginning of the planting season, solar cycle 25. And you know what a lot of farmers and a lot of people who are writing articles say? Oh, it was a one-off. It was a one-off. Never happen again. No. Sure it won't. Right? Every single one of those red arrows is a storm that's as big, if not bigger. Look how many fall in the planting or the harvest season. Look what cycle doesn't have it. Any. Cycle 24. This was the cycle we just came out of. This is the cycle that all the farmers cut their teeth on with precision agriculture. It's the one cycle, but the sun went to sleep at the wrong time. So we have built-in susceptibilities that you guys know about. You know what these are. You've lived with the sun and its mercurial nature. You guys remember cycle 19, maybe not 17, but 19, 20, 21, 22. You guys have the corporate memory of what radio propagation does during these cycles, unlike anybody else alive today. And these precision farmers, they've got cycle 24 and 25. That's it. What a difference, huh? So let's think about this super community mindset, because there's so many new insights being that we're capable of doing now. And I'm going to show you some of this. I'll see how much time I have here. I only have 10 minutes left, so I've got to be careful. So I might not be able to show you as much as I'd like. But you can look at the Android phones. They're mapping GPS with Android phones now. They have. We also are doing work with Ampere, looking at the polar caps, looking at how our Earth's magnetic shield changes, and geochron. Maybe some of you guys have the geochron timepiece. We're actually working with them to create space weather layers. But here's an interesting thing. So the radio impacts of the Gannon Storm were very widespread, and I'll see if I can play this. Hopefully it'll play. So this is the geochron down here, and you're seeing your radio contacts down at the bottom, the color-coded the same as the PSK reporter. So this should not be super surprising to you. But look at the top. We've got Ampere. So you're looking at magnetic field, basically. On the right-hand side, you see field-aligned currents. Those are the currents that cause aurora. On the left side, you're seeing all the currents that are not quiet. We've subtracted off the quiet currents. And look at that, and you can see even the aurora on the geochron map there. Look how radio propagation is changing, okay? Hopefully you can see the date. I know, again, the screen is a little small, but that's May 11th. By May 12th, you're getting short hops. No TEP, well, very little TEP, if any TEP, right? Even on the day side. And look at the United States, it gets even worse. There's almost nothing. That almost looks like a solar flare occurring. That's how bad it got. And while that was happening to you guys, this is when the farmers were trying to plant. If I look at it closer, let's just look at the CONUS for a second. Let me show you something very interesting that we're able to learn. On the left side is May 10th, when you'll see the storm start. On May 11th, on the right side, that's when the storm is ending. But look at the radio propagation on the left. A lot of radio propagation, right? Now you'll watch that storm start here pretty quickly. On the right, that storm is beginning to die down. Okay, so there's the left. You can see the storm starting. You can tell for no other reason that we can see a lot of currents and stuff here. But look at the radio propagation. Yet here, look at the right. Storm is dying down. Look at the radio propagation. So there's a massive delay. Isn't that cool that we're actually able to see that? We had strong aurora, huge currents, huge disruptions in the Earth's magnetic field, but your radio propagation was doing well still at the early onset of the storm. Whereas after everything calmed down, there still wasn't decent radio propagation. It lasted for, what, 3/4 of a day before things began to come back. So that tells you there's a huge delay in the ionosphere. That's great for scientists to understand, but it shows the power of aggregating data from different sources. Another one, this is the Android phones, and I don't have a lot of time, but I'll just play this while I talk a little bit. So on the right, again, you're seeing your radio propagation. On the left, you're seeing the Android, the total electron, what we call total electron content, which basically affects radio propagation of all sorts of frequencies. And you're seeing a big drop. It goes way down right there. And when it goes way down like that, you're actually seeing, that's when you're seeing the radio propagation, the HF radio, if I can get the arrow back, you'll see the radio propagation dip when this red lip drops way down. And we know from current, watching the current, it's actually when the current went from one direction swiftly to the other direction. It changed like very, very quickly, and it caused this rapid wave drop, and we're seeing it like ripple down from high latitudes to low latitudes. So this is what is possible today. And now here's the part where the whole super community mindset comes in. So I'm going to just let this play. So this is ROTI. This is the rate of change of that electron content, right? The electron content is what you guys care about for the layers for propagation. And this isn't scintillation, but it is a risk factor for scintillation. So green is good, yellow is red is bad. And so what you're seeing is how the risk for scintillation of GNSS signals, so this is higher frequencies, this is now the L band, right, in the gigahertz range, how those frequencies are going to scintillate, right, so twinkle, twinkle, little star, during that storm. But what I've done is I've overlaid the Maidenhead grid on it. See the Maidenhead grid? Imagine amateur radio operators being able to tell, because you guys are doing HF and doing DX, these guys only care about Starlink, or they care about GPS right above their heads. You guys know when it's coming. You guys can sense what's happening hundreds, if not thousands of miles away. And if you just report your grid square, and we got them to understand what grid squares are, and they know what grid square their farm is in, imagine how powerful that could be, right? So one of the cool things about thinking with the super community mindset is that you guys provide, not only do you guys provide the over-the-horizon and early detection arm of this super community, but you get the benefit of all of them kind of joining forces, because I guarantee you, once they realize what you're capable of doing, they're going to want to be part of the club. So there's a new ham, right, in the storm chase community. There's a new ham in the aurora chase community. I've already seen it. I've already seen aurora chasers come in, and there's a new ham. Right? And I don't know about you, but I love that new ham smell. So to summarize, right, this May 2025 Gannon Storm was the largest in 20 years, and it really opened our eyes to the new susceptibilities, especially in precision agriculture. We are now entering the declining phase when that activity increases, but F10.7 drops. So that could be a bigger, even more issues for you guys. And solar cycle 25 is going to continue to outperform its predictions. We're going to have faster streams, stronger storms. Do not use cycle 24 as your benchmark. Go back to cycle 23 or 22. That will be your benchmark, okay? Space weather impacted communities are becoming a super community of expertise and experience. And you guys lead this. And there's huge communities that are going to need this, because you're the over-the-horizon and early detection arm of the super community, and the precision agriculture community is only one of many fast-growing fields that are going to need your guidance in the coming years. So please recognize you're the Elmers to the precision ag community, among many others. And I thank you for doing what you do. So, and that's it. Considering I'm the last person, we've got 3 minutes. Anybody have questions? I'll take questions. Yeah.
Looks like about a second after, and like the preview about the movies and the risks of solar and affecting electronics, is that a reality, or is that Hollywood? Is that really a risk that there are electronics could be blown out by a solar?
If your electronics are the size of Lake Michigan, sure. Because the issue with what happens is that their electronics are in trouble, but it's power grids. They have to be massive. And the reason why is because Earth's magnetic field is only the size, it's only the strength of a fridge magnet. what makes it incredible and very effectual is that it's a fridge magnet the size of Earth. So if you integrate over large distances, then you can get the big potential drops and you can get the big currents flows and things like that. The only other, so that's why big infrastructure has problems. The only other thing that is an issue is, especially at low latitudes, you can get an E3 component of an EMP. So some of the storms that have hit Earth that are super fast, they don't even have to cause a big geomagnetic storm, a big, like what we just saw with the Gannon Storm. They can be big, what I call big bumper cars, because they can have the wrong polarity and just hit Earth really hard and cause Earth's magnetic field to wiggle like really fast, and that will actually cause an EMP. It's a slow EMP, but it's still enough to take big infrastructure out. So there's two ways it happens. But yeah, your pacemaker or your, stuff like that, the only time that's a problem is if if you have an implantable medical device. That's when you're flying an aircraft. They might have single event effects, stuff like that, but nothing from big geomagnetic storms. Okay. Any other questions, guys? Yeah. Meteor scatter. Not right now, but I'll tell you one thing that I'm really interested in is Starlink scatter. Because as these things continue to burn up at a higher rate than they're supposed to, because the cycle is bigger than they expected, and they are being chewed up. Their lifespan right now is only about 3 years as opposed to the expected 5. What is that burning up in the atmosphere? Is it creating nucleation sites and creating, in a sense, kind of like being meteors? So I'd be very interested to know if meteor scatter and sporadic picks up because of this.
We've got a professor out of RIT, Rochester, New York.
Yeah.
And he's working with our club and his students are developing a unit that we're going to hook up to AM antennas, try and catch over the horizon stuff. It's only like a 2-second blip.
Yeah.
We're trying to work with them on that.
Oh, that's cool. Right on. Yeah, I mean, we can talk about it. We can talk later if you'd like. Come chat with me and we can discuss a few things more. Love it. Sounds great. Yeah. The actual PowerPoint slides are about 800 megabytes because the movies are big. I can get you a PDF if that's what you'd prefer. Okay. Yeah, I can get them to you. Yeah, I think I'll have to talk to Tim. Where is Tim? He left. Look at that. He abandoned us. Hey, I love it. I'll be here all night. No, I'm kidding. Yeah, right. Yeah, I'm going to get him for that. We should all get him. So yeah, any other questions, folks? Yeah.
Spain, Portugal, power outages, any relation?
No. Well, let me ask you. You will know the answer to this. Did you have a problem with radio propagation that day?
I'm sorry.
Did anybody have problem with radio propagation that day? Nope. No problem. And that's the funniest thing is that they'll blame atmospherics. They'll think there are a ton of people out there that will blame atmospherics. And I said, I don't have to look or think or speculate. I just go to the amateur radio community and go, hey, how's propagation today? Anything unusual? And if the answer is no, definitely wasn't space weather related. Because again, you guys are on the front lines. What ended up happening, I actually was following that quite closely. Because unlike the one in where was it? Not Puerto Rico, it was another low latitude area in South America that had issues. But why I was watching was because I wanted to see what was going on. I am very concerned about renewables. And as it turns out, the Portugal grid, the Spain grid, they're about 80% renewables. And so they've taken a lot of the old big generators offline. And those big old generators with their spinning blades, those things create inertia, right, which gives us something called reactive power. And when you remove those from the system, then any oscillation does not get damped very well because the system can't handle it. And on top of that, the renewables decouple. When the grid starts going wonky, the renewables go, not my problem, I'm out. So it completely decoupled what little inertia that those wind turbines and everything had from the grid, and it made it worse. So these little oscillations just got completely out of control. Yeah.
This is why we should leave our radio on with the MGA running, even though we're not around the shack. Because everything we receive from these databases that you harvest.
Oh, right, exactly. That would, yeah. If you can leave it on at all times, definitely do, please. And like the WhisperNet and everything else, that's so wonderful. Yeah, we really appreciate it because we can't mine all this data. Even Nathaniel Frizzell, I pinged him just the other day about it, and I said, "Are you working on the Gannon Storm yet?" And he said, "No, we're not working on it yet. We're still doing the Eclipse stuff." So it's a personnel shortage, but the data will always be there, thank goodness, and we will get to it. So yes, if you guys contribute to any of those databases, absolutely appreciate it very much. Anything else, guys? Oh yeah.
So the implication is that some of these issues that Puerto Rico's having with their power are related to the solar event.
Puerto Rico wasn't anything to do with solar.
Though there was one, what was the, and I'm short of, for some reason I'm losing my mind. I did an interview just recently on the one that was down in South America somewhere. And what was it, Dominican?
That was Spain, Portugal.
Yeah, not the Spain and Portugal wasn't, but there was one prior to that that was actually occurring during a geomagnetic storm, and I believe it actually was. They were having trouble, and it might have been Puerto Rico having trouble again. I think it might have actually been. Was it? Was Puerto Rico? Yeah, it was recent, right? They actually had a brownout, and it was something about a branch being over, and then suddenly, like they had a cascade failure. And one branch on the tree was not going to do that. So I knew immediately from the way that they talked about it that likely a GIC was involved, because what space weather typically does is that it pushes something over the edge. So you already have a weakness and maybe a branch fell on a tree, but it should only cause that one transformer to go. Instead, they had all these relays trip, pop, 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 all the way across the grid, and it caused a cascade failure. That is typical when the grid is right at the hairy edge of going overload. And they don't have the right mitigating procedures involved because, for instance, in the United States, in the CONUS, starting at a G2 level, okay, so a moderate level storm, we have a ton of things that we do to mitigate. We actually take off all the relays, all the protective relays, we turn them off because they'll pop and they'll pull these different parts of the grid down. And when they do that, it's just like what happened in Spain and Portugal. You're taking away all the inertia, all the reactive power that you need to stabilize. And so really the best thing to do with big space weather storms, ride them out. Let the transformers run hot, because if you don't, you risk a cascade failure. Yeah.
Are those mitigation factors done at the reliability council level or at the individual utility level?
They're done at the NERC and FERC level. They've got actual procedures that they've got running. Now, how they're implemented, I don't know. I'd have to talk to Antti Polkinen. He's been doing this his whole life. In fact, I saw him a few days after the Gannon storm hit, because we all flew to Italy for a school that we were teaching, and he was doing the jig. He was so happy because he spent 20 years of his life as a volunteer teaching the NERC and FERC about GICs, these geomagnetically induced currents. And it's a labor of love, right? It's a very thankless job. But the fact that we rode through our first G5 and he got a real test of how we did, and we had problems, but the operators rode it through okay. So here in CONUS, we're actually doing better than we thought, and he was very happy. So am I. Yeah.
I had another question. All the effects you're talking about are terrestrial. Does space weather affect interplanetary stuff like moving asteroids around and things like that because of the vapor of the solar pressure and things like that?
Well, it won't move the asteroids around. It'll move their tails around like comets and stuff like that. But we have planetary bodies have their own relationship with the.
Strong enough to affect any of that stuff?
Sure, all the time. That's one of the reasons why Mars has very little atmosphere left. Because once it lost its internal magnetic field, its dipole generation, well, the solar wind started slamming straight into the atmosphere, started stripping it off. Yeah, we call them pickup ions. And so that's the reason why, and its oceans evaporated because it was replacing the ionosphere that was being ripped off. And so eventually, it'll have no atmosphere and it'll look like Mercury, eventually. That's what I mean, yeah, that's Mars. That's exactly why Mars has no atmosphere, has very little atmosphere. Although you can still do radio propagation there. You just have to change the frequencies. You can still do skywave, believe it or not. Yeah. So that's the other thing I talk about is that, you got the Mars generation, right, coming up, and they want to colonize Mars. You guys are also the Elmers to the Mars generation because you're the colonists for Earth, and you learn how to do over the horizon propagation. What are they going to do over there? There's no cell networks, right? And during inclement space weather, the layers get opaque to the satellites. You can't get signals in or out. So they're going to have to do ground wave, right? You guys know how to do that. So you're going to be teaching them too. This is what I mean. The expertise in this room is incredible. And I thank every day that I was brought into this world because you guys are fantastic.